Let's get started. So let's look at some examples of capacitor combinations. So we're still on chapter 29, section 5. So I'll just remind you of the different combinations and how to do the exercises. So recall that for capacitors in series, we have the following. So let's say you have a battery here and you connect the capacitor like that with the second one, and let's say a third one. So this is a series combination. This is C1, C2, and C3. Okay, so the effective capacitance can be written this way. So you have effective capacitance, C effective, or I think in your text they call it equivalent. Yeah, equivalent capacitance. So C equivalent, in this case, let's do it -1, or actually let me do 1 over. So 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So capacitors in series add up this way. So this is for series. And then if we have capacitors in parallel, we have the following. So we can have a capacitor set up like that. And then we have a second one. And let's say a third one. So this is a battery. And so this can be C1, C2, and C3. So the equivalent circuit looks that way. So this is battery again, and this is C equivalent. So the equivalent circuit will look this way, where we have C equivalent equals C1 plus C2 plus C3. So what this means is that the equivalent circuit has a larger capacitance than the capacitance of an individual capacitor in the circuit. So this is for parallel combination. So we can have it also. We can have a combination of parallel and series circuits, as shown below. So let's say we have again our battery, and then we can have a series capacitor this way, connected to a parallel capacitor, and we can have a series this way. So this is V. Let's call it C1, C2, C3, and this is C4. So we can condense this circuit first of all by following this path. So we can do it. We redraw the circuit. So we're going to combine first the parallel combination. So this will be C equivalent. So this is C1, C equivalent, and C4, and that's V. Okay. So the C equivalent in this case, the C equivalent is equal to C1. C2 plus C3. That's C equivalent. Okay. And now that we have the circuit as a series circuit, we can now finish it up. So we'll go to the new circuit, which will look like that. And this time it will have an equivalent circuit which looks this way. So let's say C equivalent prime, where C equivalent prime is equal to 1 over C1 plus 1 over C equivalent plus 1 over C4. So once you do it this way, then you are done with your circuit. You are done analyzing the circuit. So now we have a circuit which looks like this initially, and then we've broken it down into a new circuit, and we finished it up with the final circuit, which is the equivalent circuit for that complicated circuit we had initially. So suppose we have C1 equals 40 microfarads, C2 20 microfarads, C3 let's call it 30 microfarads, and C4 is 30 microfarads. Okay, so we can say what is equivalent capacitance of the circuit, what is C equivalent and C equivalent prime, and then we can say that what is the total charge. Let's say total charge Q. So let me give you some additional information. What is the total charge Q in the circuit when V is equal to 1.5 volts? So we'll work on this together. Okay, so let's look at the solution for this. So C equivalent, we said, would be equal to C2 plus C3 for the circuit that we have there. And C2 plus C3 is going to be 20 plus 30 microfarads. So that's 20 microfarads plus 30 microfarads. So C equivalent is 50 microfarads. And then 1 over C equivalent prime is 1 over C1 plus 1 over C equivalent plus 1 over C4. Okay, so we can calculate C equivalent prime and get C equivalent prime from that. So we shall have C4 is 40, C1 is 40, and C4 is 30. So we have 1 over 40 plus 1 over 50 plus 1 over 30. So C equivalent prime is therefore equal to what? 0.1.078. So what I want you to see from this is that the equivalent capacitance for the series combination is less than the capacitance of each element in the circuit. You can see that when we had a series combination, we were looking for C equivalent prime, and C equivalent prime is 0.078 microfarads. So the series combination makes it very small, the parallel combination makes it large. Okay, so in this series combination it's 0.078, and the parallel combination was 50 microfarads. So now we have our equivalent capacitance. So to find the charge Q, we use the relation. We use C equals Q over delta V, and we shall say that C equivalent prime is equal to the charge over the potential difference delta V. So we can say that Q is equal to C equivalent prime delta V. And delta V was 1.5 volts, so the charge stored on this whole system of capacitors is going to be 0.078 microfarads times 1.5 volts. So what does that give you? I'll give you one to try. Okay, so try that and let's see what you get. So as you're working through it, redraw the circuit each time and write C equivalent 1, C equivalent 2, and so on, so that you can keep track of it. So redraw the circuit each time as you go through it. Okay, so it looks like a lot of you are done. So let's see. So we had C equivalent to be equal to what?
0.1025
microfarads. And then the charge on the system is
0.1537.
okay. So the charge is going to be C equivalent multiplied by delta V. So you said it's what?
0.154.
0.154, and that will be microcoulombs. Well, let's check it out. Hold on a second. Let's check it out. So we can do C equivalent for C1 and C2. We'll do it for C5 and C6, and then C7 and C8, since those are all in parallel. So let's do solution. C equivalent would be C1. Let's do for C1 and C2 first. So we'll have C1 plus C2. And then we'll do C equivalent prime, which will be C5 and 6, I think. And then C equivalent double prime will be C7 plus C8. So C1 plus C2 is what?
50 microfarad.
Okay, C5 plus C6.
60 microfarad.
And C7 plus C8.
8.
Okay, so now, as I was saying, it's good to redraw the circuit. So now we have this equivalent circuit now, which would have a C equivalent 1 or C equivalent, and then this will be C3, and then we shall have C4. So this is C4, and then we shall have this circuit here. That will be C equivalent prime, and then the other one there would be this one here, which is C equivalent double prime. So this is now your new circuit after you condense the parallel circuits. Okay, so we can now add those ones up because it's a series circuit. Now we can say 1 over C equivalent. Let's say instead of double prime, let's use a triple prime. This will be 1 over C equivalent plus 1 over C3 plus 1 over C4 plus 1 over C equivalent prime plus 1 over C equivalent double prime. So you just add it up that way. So 1 over, which one is this one? 1 over 50 plus 1 over C3. What is C3? 30. 1 over C4. 1 over C equivalent. And C equivalent double prime is 80. So 1 over C equivalent triple prime. And if you like, you can do them all as decimals. So this is 0.02. This would be 0.0333. Let me know if I'm making this, if I'm doing this wrong. So you then add all this up together. Okay, so add it up and tell me what you get.
0.1025.
Okay, so it was done correctly. So C equivalent triple prime is then 1 over 0.1025, which is what? 9.75. Okay. So remember that when you add it in series, it's an inverse. So to get the actual C equivalent, you have to invert it. So what you got the first time was 1 over C equivalent prime, and then you just invert it. So 9.75 microfarads. Then we can say that C is equal to Q over delta V. Therefore, Q is equal to C equivalent triple, and then delta V. So it's going to be 9.75 microfarads multiplied by 1.5 volts. So what does that give us? 14.63 microcoulombs. Okay, any questions on that? So let's look at calculating capacitance for different types of geometries.